Hi everybody, welcome to the course on quantum theory of many-body systems. My name is Luis Dias da Silva from the University of São Paulo, the Institute of Physics. And in today's class, we're going to do a quick review of quantum mechanics. In particular, we're going to go over the single particle quantum systems, such as the harmonic oscillators. And most importantly, we're going to review or introduce, if you're not familiar with, ladder operators in the harmonic oscillators, which will be very useful for us when we talk about bosonic systems later. So let's go right in. Okay, so let's start with single particle systems. In particular, we're going to talk about what we call first quantization and what does that mean, and what does second quantization mean. We're going to go over that in a few classes. But let's start with a quantum single particle Hamiltonian. So we have a kinetic energy term here, plus a single particle potential here. So that's useful. It describes things like particles on a magnetic field under the action of an external potential, and I'm sure many of you are familiar with. So I'm already here introducing a notation that we're going to use later in other problems, which is, I'm calling the mass of the particle this m star here. This is very common in solid state systems, where we don't use the bare mass of say, the electron, but instead we use a renormalized mass, sometimes called effective mass. But for all practical purposes, this is simply the mass of the particle. And I'm also including a magnetic field here, so there's a vector potential, assuming that we have a charged particle. And this is also going to be useful for us when we talk about, say, quantum Hall systems at the end of the course. So keep in mind, this is a very generic form for a single particle Hamiltonian. Now the potential, there will be many forms here. In today's class, we're going to talk a little bit more about the harmonic potential in 1D, but this can be pretty much any physical potential for a single particle. So in order to treat this Hamiltonian and get the physical properties, of course, we have Schrodinger's equation, and here I'm writing that in Dirac's notation. So we have the time evolution of a state psi of t is essentially determined by acting with these Hamiltonian operators in the actual state, right? So this is the time-dependent Schrodinger's equation, and here's a single particle ket, right? The state that is represented. So you can view that as a vector on a Hilbert space, and to every ket there is also associated its complex conjugate, if you wish, which is sometimes called a bra. And from that we can define the inner product in this Hilbert space. For instance, a particularly important inner product is the one from the position bra here with the actual state psi of t, which gives you a wave function, a complex number, the wave function at position r and time t. And other inner products are then can be defined in position representation as an integral over a volume, the infinite volume, of the complex conjugate of the wave function related to this bra and the wave function related to this ket. Here I'm omitting the time dependence, but you can include that as well. Okay, so this is known. I'm sure many of you are already familiar with this notation. And let me just stress that this is all single particle states. And this is going to be important operator. Okay, now since we have this vector space, the Hilbert space, we can always define a basis for that. And typically we choose this basis to be orthogonal, like a base made of orthogonal vectors, and also they're normalized typically and forming a complete set of, for the basis for this single particle Hilbert space. And in this basis, the inner product between two components of the set of basis states will give you a Kronecker delta between, say, a state phi with index alpha and a state phi with index beta. This will be the delta Kronecker of delta alpha beta. And they form a complete set. So given the dimension of the basis, you can add, the ket from each of these basis states with its bra. This is, of course, a projector operator, right? Not an inner product. And this should give you the identity operator whose dimension will match the number of states in this basis set. So this gives us a very nice tool to represent wave functions in this Hilbert space. Say any state can be then represented as a linear combination of these basis sets with a complex constant here. And this constant, since this is time dependent, these constants will be time dependent, at least in this representation we are using. We're going to talk about representations later, but let's just assume that all the time dependence is included in the coefficients and the basis is fixed in time. Okay, so this coefficients can be calculated by calculating, say, the inner product of each of the basis states with the actual vector psi of t, and gives us a very interesting possibility of representing this guy here. And of course, in this Hilbert space, there also live operators. So operators, they say, like this A operator here, they act on a ket psi, right? A vector in this Hilbert space, producing another vector, right? So these are typically, they somehow change this state, producing a new one, but this is also a member of the Hilbert space. And since they're a member of the Hilbert space, there's a bra associated with that. So here is the bra, right? Is the dagger operator acting on the bra of psi, and this gives you the bra of phi, right? And you can represent both these guys in this basis set, and which gives you a interesting representation and very useful representation of this operator in this basis, which sometimes we can write as a matrix. And the indexes of the matrix are pretty much the indices of these of the basis labels, right? So given the dimension of the basis, right, the number of states in there, this will give you the dimension of these operators. Sometimes they can be infinite, but in practice we always, most of the time we tend to truncate the size of the basis, but this gives you a representation. So how do we calculate this matrix element? Well, we act with the operator on the base state phi of b. This gives me another state, right? Let's call it here in parentheses A applied to phi beta. And then we do the inner product between phi A and this new ket here. Of course, we can calculate the complex conjugate and transposed of this guy. So the dagger operator and this matrix, if you will be simply the matrix elements of a, a dagger, right? So you act on a dagger with beta gives you a bra, and then you do the inner product of this resulting bra with a phi alpha. So this is the way that you do representations of operators using this basis sets that we introduced. Okay, so let's talk about observables and Hermitian operators. So if an operator is equal to its own complex conjugate or its dagger version, we call it a Hermitian operator, right? And in a Hermitian operator, you can always find a basis which is made out of its eigenvectors, giving you these eigenvalues which are real if the operator is Hermitian. So this is a basis of the Hilbert space, which you can also write any state in this basis, right? It forms a basis of the Hilbert space. So if that's true, then we can calculate the projection of any vector in the Hilbert space, any state psi, into a given eigenvector of this operator. When you do that, we're projecting essentially this state in this eigenvector, and this has a very important physical meaning. It means that if I take this projection and calculate the absolute value square, this will give me the probability of measuring the eigenvalue A, or the value A, which is a real number, for the observable in a measurement, if provided that the particle is in the state phi. So this is what we're going to measure if you want to do a measuring targeting this operator. If the spectrum is continuous, of course, this will become a probability density, for instance, and this is a very important example. For the position operator and the position which gives you its eigenvectors are the position kets, or the position vectors, with eigenstates as its value, a real value of position r. And if you project the state psi into this eigenvector, this will give me a probability density, or not just the projection. You have to square it, take the absolute value and square it, but this will give me the probability of this state to be measured between r and r plus a small volume, right, within a small volume around this position. And so this will give me a probability density. If I integrate that over all space, this of course has to be 1, right? You have to find a particle somewhere. But this dp psi of r is the probability of the particle, if it is in a state psi, of being in a volume d3r around the position r at a given time t. Meaning that this is the probability of measuring the particle around that position. Okay, so this is important, and this only happens if I have Hermitian operators, where I can find its real eigenvalues and measure them. Okay, so let's start off with an example, very famous, very important, which is the 1D harmonic oscillator. And of course here we have the kinetic energy, right, plus the one-body potential, which is related to the position operator squared. And this is omega is the frequency of the harmonic oscillator. This is the mass of the particle. And of course, this can also describe a classical particle in a harmonic oscillator, right? And the equilibrium position is at position 0 in this case. But here in quantum mechanics, the important fact that makes it quantum, so to speak, is that these guys don't commute. The position and the momentum operators don't commute, but rather their commutator is I times h bar, right? If this was 0, I would have like just a classical Hamiltonian, but here we have to introduce these commutators and keep that in mind. And this is going to be crucial. Now let's do some tricks here and try to solve for the eigenvalues and the eigenvectors of this, well, at least the eigenvalues for these operators, which is of course a Hermitian, right? Since both the momentum and the position operators are Hermitian, so I can, the Hamiltonian here is always a Hermitian. Let me just make a comment that non-Hermitian Hamiltonians is a very active topic of research nowadays, and we can discuss that later. But in this case, of course, this is all Hermitian. Okay, so we can also, of course, write that in position representations. We can rewrite the Hamiltonian, the whole Hamiltonian in the position representation, meaning that in position representation, the action of the operator P is equivalent of that of a derivative, right, with h bar over I. Sometimes some people like to do the minus I h bar. I prefer this, is more compact for me at least, h bar over I. And typically what you do in the quantum mechanics course, you write this in position representation. This becomes a second derivative. There's going to be a minus h bar square here, and you solve this differential equation. Here we're going to do it in a different way. We're going to use ladder operators, and let's start with this definition, right? Let's just rewrite the position and momentum operators in a rescaled way, right? I'm going to choose this form, which gives us this operator big X, which is also Hermitian, as simply multiplying the position operator by square root of m omega and h bar. And I'm going to do a similar thing for the momentum operator. This should be small p. Sorry for that. I'm going to correct when I post the notes and the website. But this big P is 1 over square root of mh bar omega. Now, why did I do that? To bring the Hamiltonian into this form. So let's see how that works. Okay, so I changed the screen to this one where I can write. I'm going to do that many times over the course, right? So that we don't just use slides. So let's just rewrite this new position operator that they define, which is square root of m omega over h bar times the position, right? And then the other one, which is 1 over square root of m h bar omega times the small p. Now we want to write the Hamiltonian, which was written as this, small p squared over 2m plus 1/2 of m omega square position square, right? So we can, of course, invert these equations. And let's do that right now. And write as this. So small x equals square root of h bar over m omega times big X. Small p equals square root of mh omega times big P. That means that, let's rewrite now the, let's do it here. What happens if I take small x squared? Then the square root goes away. I just have h m omega big X squared. And this small p squared is going to be m h bar omega big P squared. Okay? So let's take that to the Hamiltonian over here. So if I then, sorry about that. This is moving. This was not supposed to be moving. Let's put it right here. So I have 1 over 2m here. Let's put the small p squared. This is going to be an m. That's going to be an h bar. And that's going to be a omega big P squared. Plus, there's 1/2 m omega squared. And then let's put the small x squared there. H bar m omega. Now, a few things will cancel. So, for instance, here, let's do this in orange. Though this one will cancel. There's going to be a 1/2 of h bar omega here, which is good. Here, this mass will cancel. This doesn't look like, but it is a mass, believe me. Let me write it better. Okay. And there's omega squared here. It's going to cancel. And I forgot to put the big X squared here at the end. All right. So these things cancel. And I'll have, in both terms, an h bar omega, right? And also a 1/2. And it's going to be a p squared plus x squared, which is right the expression that we had before. Okay. Let me see if I can go back to our example. So this is the Hamiltonian that we had, right? Okay, now the question is, how can we diagonalize this Hamiltonian? And for that, we're going to introduce other two operators, which are not Hermitian. And I'll call these operators small a is 1 over square root of 2 big X plus I big P. And its dagger version will be 1 over square root of 2 big X minus IP. Remember that both X and P are Hermitian, so A and A dagger are not Hermitian. So A is not equal to A dagger. It's not an observable, but still going to be very useful. You can always write, then of course invert these two equations and write big X and big P as in terms of A and A dagger. Big X, right? If you just add the two of them, you'll get a 2 over here over square root of 2 is going to give you a square root of 2 here. X, so X is 1 over square root of 2 A dagger plus A. P, you can do the same thing, is going to be I over square root of 2 A dagger minus A. Remember, if you take the Hermitian conjugate of both, you should get the same thing, and in fact you get, right? You get a minus sign here if you go from A to A dagger, but you get an other minus sign here from the conjugate of I, and you get the same. So X and P are Hermitian in this sense. Okay, now the idea is to substitute here in these two operators and write H in terms of A and A dagger. We're going to see how to do that. But first, let's do something else, right? Let's show two important things. One is that the commutator of X and P is just I, and that the commutator of A in A dagger is 1. So let me bring back that those notes. Let me try and okay, let's clear the whole thing and just rewrite the let's just clear everything. Otherwise it's gonna take too long to erase. All right, so let's do here. So let's just rewrite the definitions of big X is square root of m omega h bar small x, and big P is 1 over square root of m h bar omega small p, right? Oops, sorry. And we're going to do the same thing that we did there, which is small x equals square root of h bar m omega big X, and small p is square root of m h bar omega big P. Now we know that the commutator of small p and small x and small p is I h bar. We want to figure out what's the commutator of big X and big P, right? So we can do that. Well, can either one is fine. So let's do this commutator here using these expressions. So let's use commutator of big X and big P. See, the prefactors will come out. There will be m omega h square here. There's going to also be a 1 m omega h square here. And we're left with the commutator of small x and small p. So this is this, right? I just use these formulas here. Now let's cancel a few things here, right? So this is going to cancel, this is going to cancel. There will be a 1 over h bar here left. This is I h bar, right? So this is I. Okay, so this the first one we already figure out, right? And let me write here the definitions of A, which is 1 over square root of 2 big X plus I big P, and A dagger equals 1 over square root of 2 big X minus IP, right? So let's calculate then the commutator of A and A dagger. Okay, so there's going to be a 1/2, and then the commutator of big X plus I big P with big X minus I big P. This 1/2, then I'm going to have many commutators here. First is the commutator of X and itself, which is of course 0, plus I, the commutator of P, big P and X, then minus I, the commutator of X and big P, Then I and minus I is plus commutator of P and P. Okay, so a few things will cancel out here. This one is 0, this one is 0. This one is I, so there's going to be a I here. And this one is, of course, minus I, since it's minus the commutator of X and P, right? Okay, now we get something interesting here. We have 1/2. I and minus I will give me +1. Minus I and I will give me another +1. So this is 1, right? So I just proved these two commutators. You can also show that age is written in terms of age A and A dagger as this. This factor of 1/2 is very important. So let's try to do that so that you have an idea. Yeah, let's erase something here. I'll keep that so don't have to write it down again. Yeah, let's see. This takes a long time, but okay. I have to figure out what takes more time, to rewrite that or just erase this. I think it's just. So we showed before that the Hamiltonian. Oops, sorry. Okay. So we showed before that the Hamiltonian is square h bar over 2 x squared plus p squared, big P, right? Now we know that we can invert this. Let me write it here, small, but big X is 1 over square root of 2 A plus A dagger. And big P is, there's that I, square root of 2 A dagger minus A, right? So let's just write that. This is going to be square, right? So there will be a factor of 1/2 here. So A plus A dagger. I'm going to omit the hat here, times A plus A dagger. Here there's going to be a minus 1/2, sorry. Let's erase this. A minus 1/2. What was that? No, I want that. Yes. Thank you. Minus 1/2. Why? Because there's I here. When it's squared, it's going to be minus. A dagger minus A dagger minus A, right? Someone let me erase something else here. We get just more space. Let's try to find a way to get okay, let's go back. So this is h bar over 4. Let's take these two, and now let's see what we get here. Here we get A times A plus A dagger times A plus A times A dagger plus A dagger times A dagger. Here you have this minus, right? So let me just do here so that I don't get mixed up with a minus file. A dagger minus A dagger A minus A dagger plus a. All right, so let's keep going here. H over 4. We get this is going to be, let's already start canceling things out. This one is going to cancel this, right? Because I have this minus here. This one also will cancel, but the other ones will not, right? So what we get, so I have 2, so there's going to be a 2, a dagger a, right, from this and this, plus 2 a dagger. Now I know that the commutator, and this is just the result, I'm gonna write right here, a dagger equals 1, meaning that a dagger minus a dagger a equals 1. Let me erase some of that too. Try to figure out how to get a big eraser and erase a big part of this. Okay. All right, so let's keep going. Just one final step. Oh, so there's this factor of 2, h bar over 2 now. So I'm just going to simplify this with this. There's going to be a 2 here. All right. And then I'm going to use this. That this is essentially 1 plus a, and this is just one plus h bar h. All right. Now I get this. I'm going to move the 1/2 inside. 2 a bar, sorry, plus 1/2, and I get exactly the expression that I'm looking for the Hamiltonian. Okay. All right. So this is the expression for the Hamiltonian, and in today's assignment, you will show that the commutators of a and a dagger are 0. Right? And you also show that we can define a number operator, which is a dagger a, and of course it will commute with the Hamiltonian. And this operator, which is this one, is Hermitian, right? You can show that. So it will have eigenstates that are integer, and that you also have to show that they are not only real, but they are integer. That's an important step here, and in the assignment is your task to do that. And if this is an integer and the eigenstates of n will also be then eigenstates of h, since they commute, we can show that the eigenenergies of h are precisely of that form. That when I apply, and this is the other thing you're going to show, that when I apply h dagger into these eigenstates of the number operator n, this is not an eigenstate of a dagger, but rather it takes you to the next one, the n+1 state in this sequence, with an eigenvalue, well, not an eigenvalue, but with the resulting of these operators square root of n+1. You're also going to do that, and you can in fact use these operators to go and applying from the operator 0 on and build any eigenstate n here, and it'll give you the energies, which will be h bar integer plus 1/2. These are the energies of the harmonic oscillator. So this construction is usually done in a graduate quantum mechanics course, so I'm just reviewing it here. But the fact that these guys have these interesting commutation relation will be important for us later, so keep that in mind. So now what I have the single particle spectrum for the Hamiltonian. So I start with n equals 0, right? This is the ground state. Notice that the energy of the ground state is not 0, but it has, this finite value, h bar omega over 2, right? That's the, sorry, this should be over 2. H bar omega is the differences between the different levels, right? This should be over 2 here, sorry. And then this also produce an orthogonal basis, orthonormal basis for the single particle Hilbert space is spanned by these vectors. So you can, in fact, show that these guys are orthogonal to each other, and they do form a complete set, and they are eigenstates of the Hamiltonian, right? That leaves us to a way to express any single particle states in this Hilbert space, the single particle Hilbert space, as a combination, a linear combination of harmonic oscillator operators. And in fact, if you write them in terms of in real space, right, in configuration space representation, this will give you those Hermite polynomials and all that is usually done in the undergraduate quantum mechanics course. And you can write any function and in terms of these eigenfunctions of the operator. So here I have, for a given state, I can project them into one of the eigenstates of the harmonic oscillator. It doesn't have to be, can be any state. But if I want to measure, say, what's the probability of measuring a given energy of this Hamiltonian for this particular state, right? I essentially can project this state into the energy eigenstate, take the square, the absolute value square, and this will give me the probability of measuring this value of energy in this state. All right, so this is essentially the review of quantum mechanics. So this is all single particle. I cannot stress that enough. And in the next class, we're going to do many particle systems and see how it pans out. So for the assignments, they are on the webpage of the course. There are 2 problems for the harmonic oscillators. Essentially, the one that we're going to prove these steps here, and most importantly, show that this is the eigenstates of these number operators are the eigenvectors, and the eigenvalues are not only real, but they are integer, right? And then the problem 2, you're going to solve a slightly different Hamiltonian with this term here. I would like to have a physical interpretation of what this term means. And I'm already calling these operators bosonic. This will be more clear when you talk about second quantization. Okay, so that's it for today's class, and I'll see you in the next class. See you.